All right, our only question for homework last night was this question where we have two objects, a 12 kilogrammer and an 8 kilogrammer, connected together by a rope. We wanted to find the tension that joined these two objects together. This is a question that is at least partially based on questions that we've been doing over the last 4 or 5 days. This is the multi-force problems, draw a free body diagram, calculate the acceleration based on the net force, based on all of these individual forces adding together. But it's also, at least in part, a Newton's third law problem, where if object A applies a force on object B, B applies an equal and opposite force on object A. It's a small connection to Newton's third law, but it is a connection. Let's tackle this. What's the first thing that we're going to do when we're analyzing this problem? Yep. Yeah, we got to find the acceleration. Now, remember the analogy that I gave you yesterday with the ice cream truck, right? You got this trailer being pulled by a tractor. Okay, the tractor is the cab of the semi-truck, right? So the trailer is being pulled by the tractor. Now, it pulls it with a certain force. Okay, that would be the equivalent of the 45 newtons that we're pulling the trailer with. Now, inside the trailer is going to be a bunch of pallets of ice cream, maybe a 12 kilogrammer and an 8 kilogrammer. When we're analyzing this to find the acceleration of the trailer, we don't pay any attention to the forces in between the ice cream pallets inside, right? There are forces. Okay, one pallet pushes up against the next pallet, and there's going to be forces in between them. But we don't pay any attention to that if we're just looking for the acceleration of the system, of the trailer itself. So what I want to do here in analyzing the system is pretend that we have one object. It's a 20 kilogram object. Forget about the fact that it's 12 and 8. If I'm analyzing the trailer, the whole trailer, then I'm going to use the mass of the trailer and all of the ice cream that's inside the trailer. So let's do that now, pretending that there is only one object here. We're going to say the net force, since we already have my free body diagram drawn, is going to be equal to, I'm going to call this FF1 plus FF2, the force of friction on the second object, plus the applied force, which would be the equivalent of the force that the tractor is pulling the trailer forward with. All right, the net force is also equal to m times a. What mass do I use here? 12, 8, or 20? Dryden, which mass do I use? 12, 8, or 20? No. Isaiah, which mass do I use here? What's the force of friction? 12, almost. Yeah, you could, you know what, you could say 30. Okay, you could say neg 30 and combine them. That would be okay. I'm going to choose to do them separately, but in the end, it doesn't really matter. Okay, I'm going to do them separately because they're labeled separately. If I'm going to do them separately, I'm going to say not 18 and 12, but neg 18 and neg 12 because they're to the left. And then the applied force is what, 45 newtons? To the right. So what do we got here? 20 times the acceleration equals neg 30, 15. And A is going to end up being equal to 0.75 meters per second squared. All right, there we go. This is a problem that we've done many times before, just not in the context of needing it to do something else. Okay, most of our problems that we've done like this have been finished at this point once we found the acceleration. All right, that's the acceleration of the system, but it's also the acceleration of the 12 and the 8 kilogram box inside the system. Simon, you got a question there? What do I do with this now that I have the acceleration? Now I'm looking for an internal force, right? I'm looking for the force between pallet 1 and pallet 2 inside the trailer, not the forces acting on the trailer itself. Yeah, go ahead. Draw another diagram for what? Okay, sure. Yeah, let's draw a free body diagram for one object. Now, Simon suggests that we draw it for the 12 kilogram object. Let's do that. Here's the 12 kilogram object. It's another free body diagram, right? There's a force of friction to the left of 18 newtons. I'm calling that FF1 still. Now, really, I could just call that FF because there's only one friction force now, right? But I just want to be consistent. So I'm going to keep calling it the same thing as I called it before. Now, what are the forces we have acting here? Force of tension. We know that's going to be a bigger force, actually. FT. Why do we know that's going to be bigger? Ashton, why do we know that that force of tension in this rope is going to be bigger than the force of friction pulling this 12 kilogram object backwards? Yeah, no, it doesn't have to pull another 8 because it's the 8 pulling on the 12 with this tension force. So 45 is pulling on the 8, and then something else is pulling on the 12, and then the 12 is being pulled backwards with 18. But how do we know that that tension has got to be bigger than the force of friction pulling it backwards? Is it? Yeah, if it's moving to the right, the net force has to be to the right on all of the objects, including the 12 kilogram object. So let's say F net is equal to the sum of the forces again. This time it's FF1 plus FT. Mass is 12 this time. Acceleration is 0.75. FF1 is negative 18, just as it was before. Now we're going to solve for FT. 12 times 0.75 is 9. 9 plus 18 is 27 newtons. No, it'd be positive because the 18 goes over by adding, gives me positive 27 newtons. Now, is there a way to get negative 27 newtons when you solve this problem and correctly get negative 27? Sure there is. How would I have gotten that, Isaiah? Yeah, if I had to use the other object. Is it legitimate to pick the other object? Of course it is. It doesn't matter which one you pick. Let's try that now, just to see what we end up getting, to justify that we do end up getting 27 newtons either way. It's 8 kilograms. We have kind of ran out of space there, but we have an applied force of 45 newtons to the right. What else we got acting on this 8? Friction acts to the left. FF2 is 12 newtons. Anything else? Yeah, we have FA, the force of the rope. Because we know that if that 8 pulls on the 12, then the 12 pulls on the 8 with an equal and opposite force. So we're going to say that's FT. F net, there is gravity and normal force acting on all of these, right? But why didn't we draw those in? Why didn't we pay any attention to them, Quinn? Well, gravity and normal force mean something, but yeah, not in the equation because they cancel. Yeah, because they cancel it. They're balanced and they cancel it. F net is equal to FT plus FA. F net is 8 times 0.75. FT is what we're looking for. The applied force, I'm missing one. FF2. FF2 is neg 12, and FA is 45. So 8 times 0.75 is 6. On the right-hand side, we get FT plus, what is that, 33? The 33 goes over by subtracting, and what do we get? 27. No, not 27. Negative 27, which we would have predicted, right? Because if the 8 pulls on the 12 with positive 27, then the 12 has to pull on the 8 with neg 27. And there's your tie into Newton's third law, right? Object A applies a force on B, B applies an equal and opposite force on object A. If you get a quiz or a test with a question like this on it, what's a good way to check to see if you've done this right? If you have time. Do it both ways. If you do it both ways and you get the same answer but opposite sign, like you have to be right. Like you almost have to be right. The odds of you being wrong are minuscule. But if you get a different answer doing it both ways, the odds of you being wrong are 100%. You must be wrong if you get a different answer there. Now, we do get a negative and a positive, right? Okay, of course, we have to expect that difference. And listen, I don't care which one you give me. Okay, tension of the rope is technically a magnitude thing. Okay, so we would say it's 27. But if you make it negative 27, that's fine. I'm not going to take off marks for that. Go ahead.
This probably is not right, but it just happens to work out that.
All right, if you guys feel comfortable with that, let's give you one more question here. Same type of thing, except this time we've got 3 objects. We're going to still find a force of tension, but it's specifically this force of tension between the 10 and the 20. See what we can do with that over the next few minutes, and then we'll do it as a class. What's the first thing we want to do here? Yeah, we want to analyze the system, and we want to get the acceleration of that system. So let's do that. Let's say F net is equal to the sum of those forces. It's going to be FF1 plus FF2 plus FF3, because all three of these act externally on the system, friction between the 10 and the ground, 20 and the ground, the 20 and the ground. But we also have this applied force that acts on the system. It's acting directly on the 20, just as this 30 is acting directly on the 10, but it also contributes to the motion of the system. Now, what mass do I use here for the net force? The 10, the 20, or 50, the combined mass? This time we're going to use the 50, the combined mass, because we're analyzing the system. We don't know what the acceleration is. That's what we're looking for in the short term. FF1, Dryden, what's FF1 going to be equal to? Nope. How about negative 30? Negative 30 because it's to the left. FF2 is going to be, Max, what's FF2 going to be? Yeah, well, negative 60, right? Because it's to the left. Jackson, what's FF3 going to be? Yeah, negative 60 because it's to the left as well. And what's FA? What's FA going to be, Dryden? Good. 200 newtons to the right, positive 200 because it's to the right. Good. We want to find A now, so let's combine some terms here. 50 on the left side. Add all these up on the right side. We end up getting 50. So 50 divided by 50 gives me 1. The acceleration is 1 meter per second squared. Now, that's not my final answer, but that's a big step in getting my final answer. Listen, we know if the system accelerates at 1, then we know each of the individual objects within the system also accelerate at 1. Now what we want to do is what? Pick an object. Now, technically, it's correct to analyze any of these objects, but you're going to find that it's not convenient to analyze 2 of them. So you're going to pick one of them that's going to work the best for you. Which one's that going to be? Sebastian, which one do you want to try here first? Yeah, the first 10 kilogram object, sure. Now, if I happen to have picked one of the other ones, it's not the end of the world. You're not going to get the wrong answer. It just means that you're going to make it either harder or you're going to end up with a couple unknowns and not be able to solve for them. If I pick the 20, my problem there is I've got 2 tensions, this one that we're looking for, and this one, neither one of which I know. So that's 2 unknowns. If I pick this one, all right, that's fine too, but then I'm solving for a tension that I'm not looking for, which is fine, but it's more work. So I'm going to pick this object. It means I got a 30 Newton force acting backwards, FF1, and I've got a tension acting forwards. I'm going to call it FT. I'm going to say F net is equal to the sum of those forces, FF1 plus FT. This time it's 10 times the acceleration, but we know the acceleration is 1. FF1 was 30, right? Yeah, we're going to make it negative 30 because it's acting to the left. I don't have to label it as negative on my diagram because the arrow shows the direction. In my math, the negative shows the direction. We add that to FT. 10 on the left side, add 30 to that, it gives me a tension of 40 newtons. How many people got 40? Okay, if you got 40, did you do it this way? Anybody do a little bit differently? We could have analyzed this and found this tension, and then we could have analyzed this, knowing this tension, to find this one. But it would have been twice as much work, right, on the second half of this. Okay, not wrong, not worse, just more work. All right. Here's some check and reflect questions on page 168. We'll give you a little while to work on these in class here. All right, I want to jump forward here and do some more multi-force problems, but these ones are going to be a little bit more specific examples of multi-force problems. We've done some general things where object is being pulled by a force to the right, by a force to the left, and so on. These are going to be specific situations. Same type of thing, but just a little bit more specific than what we've been doing thus far. First one is the one that you see up on the board here. This is what I call an elevator problem, because we got somebody standing in an elevator with forces, vertical forces acting on this person, as opposed to that general situation where we have force to the right, force to the left, and so on. I want to draw a free body diagram of this person standing in the elevator. What's it going to look like? There's going to be a guy inside a box. What forces are going to act on the guy? Now, listen. What forces act on the guy, not what forces act on the elevator. Okay, we don't want to know what forces act on the box, the elevator, because that's not what we have information about. We want to analyze the guy inside the elevator. What force or forces act on that guy? Max, give me one of them. Good. Normal force acts up on the guy. And that normal force is provided by what? By the floor. Right? The floor pushes up. Remember, we defined the normal force as the force of the quote floor or ground pushing quote up at 90 degrees. This is the floor pushing up at 90 degrees. Now, if we're analyzing the elevator itself and not the guy inside the elevator, then what would provide the normal force then? The cable. Yeah, the cable is pulling up on it then. Okay, that's not what we're doing though. Okay, we're analyzing the person inside. What's pushing upwards on the person? The floor of the elevator. What pushes upwards on the elevator? The cable. All right, we know that, what else we got here? Nick, what other force or forces do we have acting on the guy? Okay, good. I like that, what you just said there. There's a greater force pushing it upwards because it's going upwards. But wait, it's not going upwards, is it? It's accelerating downward. Okay, so, but your logic is good there. You just misread a word, that's all. It's going downward. So there's got to be a greater force downward, right? What force is it that's pushing it downwards? Sure it is. Yeah, gravity is always acting downwards on it, right? And we know that that downward force of gravity is bigger than the upward normal force because it accelerates downward. Not because it moves downward, but because it accelerates downward. If it was moving downward at a constant speed, what would we know about those two forces? They balance. Because things keep going at a constant speed when forces balance. All right, there's my forces. With what force does the elevator push him up? Well, let's say F net is equal to the sum of the forces, Fg plus Fn. What are we looking for in that situation? Which variable, F net, Fg, or Fn? Actually, which force are we looking for, F net, Fg, or Fn? Yeah, the force of the elevator floor is Fn that we're looking for. F net would be what, 73 times 2.0? Force of gravity would be 73 times 9.81. Is that right? Not quite. Oh, but it's almost right. What am I missing there, Dylan? What's wrong with what I just did? 73 times 2 for the acceleration. That looks right. The acceleration accelerates downward at 2, right? 73 times 9.81 gives me gravity, right? Jade, what's wrong? 2 has to be negative. What else is wrong? The 9.81 has to be negative as well. Does that make sense? Downward forces, okay, downward accelerations. Let's solve for F and N now. That's going to be equal to what? 73 times neg 2 is neg 146. 73 times neg 9.81. Not sure what that is. Let's figure it out. $716.13. And we're going to take that over to the other side by adding. And we end up getting, what? 570. And we're going to round that to 2 digits. Fn is equal to 5.7 times 10 to the 2 newtons. So what do we got here? The force of the floor pushing up. The elevator floor pushing up is 5.7 times 10 to the 2 newtons. that okay? You guys okay with the math there? What's the man's actual weight? How heavy is he? Don't make this harder than it has to be. No, not 73 kilograms. That's his mass. So make it harder than that. What is it? What is it? No, that's not how heavy he is. The normal force is not how heavy he is. Guys, listen, think back to the beginning. Think back to the beginning of, I think it was last week, we talked about, or towards the middle of last week, we talked about different types of forces. The first one we defined was weight. Weight is defined as the force of gravity, which is mass times 9.81. So the man's actual weight is going to be 73 times 9.81, force of gravity. We're going to make it positive because I don't like to have a negative weight. What do we get there? 7.2 times 10 to the 2? Newtons, yeah. Because weight is a force, right? So it's got to be measured in newtons. Remember, difference between weight and mass. Mass, kilograms, the amount of matter you possess. Weight in newtons is your force of gravity. Mass times 9.81. Yep. Because the people that make up your driver's license don't know the difference. Yeah. Well, listen, when's the last time you ever accused the government of being smart? All right, there you go. There you go. Any government, not just this government, any government, right? What is the normal force acting on the man? Boy, you don't want to make this one harder than it has to be. 5.7. Yeah, look, we just calculated that, right? We found the force of the floor pushing up. We said that was the normal force. We've already got it. What's the apparent weight of the man? How heavy does he feel? 5.7 times 10 to the 2. Remember we said weight is the force of gravity. Apparent weight is the normal force. So look at this. He weighs 7.2. He feels like he weighs 5.7. So he feels lighter than he really is, right? Now he feels lighter than he really is. Why? Because he's accelerating downward. You ever in an elevator? The elevator starts dropping, and you feel like your stomach is going into your throat. You feel lighter as it accelerates downward. Yep. Yes. Absolutely. Absolutely it would. It would be easier to do weight exercises because everything traveling with you would feel lighter. Okay? To the extent that, I mean, look at what would happen if we made the acceleration neg 9.81. Okay, right here, instead of neg 2, you're accelerating downward at neg 9.81. In other words, the elevator cable has broke. And you're accelerating downwards at the rate of gravity, right? This becomes 7.2, neg 7.2. This is neg 7.2. Take it over by add. We end up getting an Fn of 0. The normal force would be 0. In other words, you would feel weightless. You would also feel as if the weights you were trying to lift were weightless. So it would be, you wouldn't have to do any work to lift those big heavy weights because they're not heavy anymore. Yeah, but so would you. You'd be going down with it, right? Have a look at these two questions, please, on page 152. Now, page 152 relies on an example that we didn't do. So I'm going to give you the mass of that person and the elevator, 600 kilograms, 6.00 times 10 to the 2 kilograms. Now, understand in question 1 and in question 2, we're not analyzing the person inside the elevator, right? We're analyzing the elevator. So the normal force in question number 1 would be what? Not the value of it, but not the force of the floor pushing on the person, but rather the force of the cable pulling upwards. Call it FC if you want instead of FN. I choose to still call it FN. You call it whatever you want, as long as you recognize that there are two forces acting, FN and FG, or FC and FG if you'd rather call it that. Okay, let's see what you can do. Okay, number 1. We won't finish number 1, but we'll at least draw a diagram for number 1 here, all right? There's a person in an elevator. Well, we got an elevator force. We got a force of gravity pulling downwards on that elevator, right? Now, listen, we're looking for the forces on the elevator, not on the person inside the elevator, right? I don't care what's inside. Maybe there's a person inside. Maybe there's that 400 kilogram mass set inside that you're going to show off and try to lift. But it doesn't matter what's inside. Okay, what matters is that the elevator has a, and whatever's inside has a certain mass of 600 kilograms. We know that there's also a force of a cable pulling upwards. The force of the cable upwards is going to look something like this. I'm going to call it Fn, but you can call it Fc if you want for the force of the cable. It doesn't really matter. Some people don't like that term because the cable doesn't really, it's not really like a normal force. I just keep calling it Fn to be consistent with my other elevator questions. It doesn't really matter though. Now, here's what a lot of people were doing. A lot of people were either drawing another force down here upwards or another force down here downwards. It should be neither of those green forces, neither of them. Why? Because if you picture this elevator, there's only two things acting on it. Gravity pulling it down and the chain pulling it up, or the cable pulling it up. What else acts on it? The force of the elevator floor? No, you can't have the elevator floor acting on the elevator. The elevator floor is the elevator. Okay, that's like saying somebody's pushing on you. Okay, somebody's pushing on your hand. Oh, I've got the guy pushing on me, and I've got on my hand, and I've got my hand pushing on my hand. Like your hand can't push on your hand. Your hand is your hand. Okay, the elevator floor can't push on the elevator because the elevator floor is the elevator. Now, we used the force of the elevator floor in a previous question, but that's because we weren't analyzing the elevator itself. We were analyzing the person inside. The elevator floor does push on the person inside, but it doesn't push on the system, the whole thing. It's kind of like an internal force. This is what we've got. Okay, that's all we've got. Now, just a little note here. This force of gravity is not 9.81 like a lot of people are making it. This force of gravity is what? M times 9.81. So we're going to make it M times G. Now, technically, when we go to plug it into our equation, it becomes negative, right? Because it's acting downward, unlike the normal force, which is positive because it's acting upwards. Okay? Give you another couple minutes to work here, and then I want to do in its entirety question number 2. Question number 2. An electric chain hoist in a garage exerts a force of 2850 upwards to remove the engine from a car. The acceleration is 1.5 upwards. What's the mass of the engine? Tough question here. Here's the mass of the, here's the engine. It has a mass, that's what we're looking for. There's a force of the chain pulling upwards. I'm going to call it Fn, but you might not like that. You might want to call it Fc. That's fine. I don't care what you call it. I'm going to call it Fn. There's a force of gravity acting downwards, which is M times G. Why did I draw that shorter than the normal force acting upwards? If it's accelerating upward, the normal force upwards has to be bigger, or whatever force you call it going upwards must be bigger. All right, F net is equal to the sum of the forces. You might not know how to solve for M here because we don't know what M is, right? Might not know how to solve for M right now. That's okay. Don't worry about that. Just do what we do. F net is the sum of the forces, which is Fn or Fc, whatever you called it, plus Fg. We're going to say M times A is equal to the normal force plus the force of gravity. All right, what's mass here? We don't know. A is 1.5. Fn is 2850. Plus, well, Fg is M times neg 9.81. I'm going to change the order of this a little bit to make it look a little simpler. 1.5 M equals 2850. Subtract 9.81 M. Is that okay? Is that the same thing? Sure it is. And I didn't even need to do that. I just did to make it look a little tidier. Here's a question for you now. Who's ready for this? Okay, here we go. What's 1 M? Sorry, what's 1 apple? What's 1 apple plus 2 apples? 1 apple plus 2 apples is equal to 3 apples. Okay, got it? Everybody got that? What's 1m plus 2m? 3m. Okay, if 1 apple plus 2 apples is 3 apples, then 1m plus 2m is equal to 3m. Okay, listen. If 1m plus 2m is equal to 3m, then what's 1.5m plus 9.81m? Do you see what I've done there? This was subtract 9.81m. I took it to the other side by adding. So I added 9.81m there. Add those up, we'll get 11.31m. Listen, 1m plus 2m is 3m. 1.5m plus 9.81m is 11.31m. It's the exact same thing, except the numbers are just a little bit more complicated. See how I combine those terms? Now this is easy, right? Divide both sides by 11.31. 2850 divided by 11.31, and we should get 252 kilograms. Curious if anybody got that. Yeah, you got it, but I gave you a little bit of hand. That's okay. That's a good question, eh? It's a tough question, but it's a good question. Wouldn't be so bad now. Like, it's like all of them. Once you see them done the first time, it ends up not being so bad, right? There's a worksheet going around right now. There's 4 questions on that worksheet. Your homework tonight is the first 8 questions that I assigned earlier today. You worked on those in class for a while. You might be done or almost done page 168, number 1 to 8. In addition, I want you to do questions 1 and 2. 1 and 2 on the worksheet that's going around right now. 4 questions. Don't worry about the last 2, just questions 1 and 2.